We're only getting about 25 mils on the dip. During my novice part 2 video, the 1960s through the early 70s novice video, I'd shown this empty box of the WN1LRK QRP transmitter that was built during his novice years, and there was a lot of interest. I got some emails about this thing, and I think some people were kind of feeling sorry for the empty box, so that got me thinking that maybe we should build this thing. And I've got a whole bunch of junk box parts here on the table. I think we can use some of this to try to stuff some of these holes and get this transmitter back on the air. We'll use the original 5763 type circuit. It'll be just for 40 meters. I think we can start to build this. Let's look at some of the parts I've been able to scavenge. A variety of fixed capacitors. It calls for actually 3 chokes. 1, 2, 3. That's pretty luxurious for a one-tube transmitter, but this one is just for safety on the output in case this capacitor fails. That pulls the output to ground. It has no electrical function other than that. It's a safety device. So the one that's in the Colpit circuit, I'm going to try to use some smaller values. This is probably 0.5 millihenry. See if I can get away with that. The choke on the plate, similarly, we probably don't need a full-size 2.5. Maybe we can get away with a 1 millihenry choke. On the back, it has a place for a fuse. I have no idea why he put a fuse in this thing, but I'll do the same thing. We'll add the fuse. It's got the antenna connector. I'm going to take that up to an SO239. And then it's got the receiver. I have no idea how he did the TR switching in here. We're going to leave that off and do the TR switching external. Crystal socket. It appears to fit the smaller crystal socket for the HC6 style. Not sure. I've got an old broken crystal socket here. I may just use this instead so we can put FT243 crystals in it. Anything else interesting? The plate tuning, I've got a 100 puff cap here we'll use for plate tuning. It's 50 or 100 puff, I don't know what it is. And then on the loading, since this is a pi output circuit, I don't know if he used a loading cap that was fixed. You could probably get away with a fixed 470 puff for 40 meters only, but I'm going to add this this old thing on the back, and we'll use this. Looks to be about 150 puff type, and we'll put a 330 or a 470 puff in parallel with it for our loading on the output. The meter is going to need a shunt resistor since this is a 1 milliamp meter. Let's start stuffing the holes. Okay, we'll take a quick look at the progress here on the back of the transceiver, or the transmitter. On the back of the transmitter we have the fuse, which I'm not sure what I'm going to do with it, but it is mounted. We have an antenna connector, and where the receiver connector went, we have the loading control. And then on the front, we've got the tuning capacitor for the plate. Crystal socket is mounted. Key jack is mounted. The transmit test push button is mounted. On-off switch. The power lamp. Now here's something I just noticed. It says RF on the DC millimeter, so he must have had some kind of semiconductor diode on this thing, and you basically tune for maximum. I'm going to try to make it work as a actual plate current meter. We'll see how successful I am. So next we have to figure out how to mount the tube socket. So it's always good to go over the whys as well as the whats. I have mounted the tube horizontally. We talked about that before. But why in this particular orientation? Well, first of all, it makes it easy to change the tube. But more important, we want to have the tube pins located close to the area where we have the crystal socket, the key, and the main tuning capacitor. So all of the all of the tuning is going to be done in this area. We want to have the grid, pin 8 and 9, as close to this, this tuning area as possible. Over here is where we'll put the output coil closer to the output connector to give a little bit of isolation. I've used a pretty stout piece of aluminum that I bent into an angle to mount the tube to minimize any vibration. So we're getting there with the little transmitter. I've got a solder lug on one side of the socket. Really, we could put 2 lugs, one on each side. We'll need some good grounding points. But this is just showing the style of construction. This is going to allow us to replace the tube easily. The tuning output coil will be probably in this area between the 2 capacitors. So as you can see, we're trying to build up a little bit of isolation between the grid side and the plate side. Also, you can see pins 8 and 9 are the grid on the 5763. Orient the tube socket so that 8 and 9 are closest to the crystal. That way we don't have a lot of wires crossing each other. So it's good to see the whys as well as just drilling holes. Makes life easier if you do a little planning up front rather than just start blasting and drilling. Now, one thing we have to accomplish is turning the 1 milliamp meter into a 100 milliamp meter. So we've got the digital multimeter set in the ohm scale, and I'm just going to put the meter across the meter, so to speak. And it has settled. As you can see, it is reading 0.2 milliamps on the meter, and on the multimeter we're reading 81 ohms. So the meter has a resistance of 81 ohms. So we measured the meter and we found it to be 81 ohms, and we know that we want to have the meter read 100 milliamps instead of 1 milliamp. And we're just going to use Ohm's law to figure out that 100 milliamps on the meter. First thing we're going to do is take the 81 ohms and we're just going to multiply that by the 1 milliamp. 81 millivolts basically. So we take the 81 ohms, multiply it by 1 milliamp, and that gives us 81 millivolts. So 81 millivolts represents full scale on a 1 milliamp meter. We take the 81 millivolts and we divide it by what we want, which is 100 milliamps. So that's 0.081 divided by 0.1, and you end up needing a 0.81 ohm shunt. Close enough. So I took some resistors, various resistors I had, and I got a couple of them together and got close to that. Very hard to measure on a meter, but I made a shunt and I put the shunt across the meter. Now in this setup, we're coming out of an ordinary power supply. I've got a resistor in series to limit the current for safety, going into the positive pole of the meter, and then we're coming out of the negative, and we're going into the ammeter that's built into the meter, the multimeter, and then we're going back into the power supply. That way we can see how effective our shunt was. So let's start increasing the voltage and see if we can get some current to flow. Okay, current is flowing. Let's take it up to 40 something. Okay, so we're reading 43 milliamps on the multimeter, and our analog panel meter is reading about the same. It's a little low. Let's keep going. Okay, here this should be like 70, 74. Again, we're off just a little bit. The meter's just a little bit low, and go up to the full 1. Yeah. So I'm going to declare victory with this homemade shunt that's made out of a bunch of small resistors. And you're going to say, well, what if I don't have a bunch of small resistors? There's a second method we can employ that might make it a little easier to get the meter to read correctly without going to the trouble of trying to make it 0.81 ohm. So here's method 2. This is called the voltmeter method. Instead of very carefully choosing a shunt resistor, we're using an ordinary 10, 4.7 or 15 ohm resistor. And the current's going to go through that resistor and it's going to build up a voltage across it, a much higher voltage than the 0.8 ohm resistor. We'll take some of that voltage and apply it to the meter. We can do that through a voltage divider or just simply a series potentiometer going to the meter. So now we have an adjustable system. It's a voltmeter in effect coming off, and I have a little trim pot. I can adjust the scale to what I need. So let's set it right there. Now we'll bring up our current, okay, around 40. Okay, 60. Okay, it's a little high. I don't like that. I want to bring it down. I want to increase the meter now, so it's reading more like 67 instead of 60. So I just get on my trim pot now. I can bring it up just a hair. Okay, be able to adjust it. Let's go up a little more. Let's go up to 80. Yeah, see, we're right on the nose now. So anyway, that's for the perfectionists. If you want to use that method, rather than building a shunt, I'm using an ordinary 10 ohm resistor and a little 5K pot. Now you might be wondering how we're going to figure out the coil. Remember, the coil's job is to take the impedance of the tube when it's fully loaded and transform it down to 50 ohms on our output. A very crude estimation of the impedance of the 5763 is to simply take the voltage and divide it by the 100 milliamps. Well, actually not 100 milliamps. We're only going to load it to 50 milliamps. So take 350 and divide it by 0.05, and the answer is 7K. 7,000 ohms is what the tube's going to look like, 7,000 ohms. So we want to transform 7,000 ohms down to 50 ohms, which is our antenna impedance. And we'll estimate our Q on the coil, something like 15. And it's pretty easy to achieve a loaded Q of 10, 11, 12, up to 15 with a coil of this type. This is a 1-inch pillbox. We've got 20 turns on there. And with a pi network, that turns out to be around 8 microhenries is what we require, and about 60 puff on the plate capacitor, and on the output we're going to need something like 680 puff here on 40 meters. So what we've got is a 100 puff capacitor, so that's got enough range on the input side, on the tube side. On the output side we have a 470 and what looks to be about a 200 puff capacitor. It might be a little shy on the loading, but we're going to be close. Now how do we know if we're in range? Again, our handy grid dip meter, it isn't really a grid dip meter, right? It's a gate dip meter, or it could be a base dip meter, whatever you want to call it, but this is a transistorized dip meter. Turn that baby on, set it for 7 megahertz, put it near the coil, and let's watch and see if we can get a dip here. There it is. There's our dip. It's just a little beyond mid-range. Perfect. That's what we want. So we know that we have a good pi network that should do the job. I haven't decided what I'm going to do with this switch. I haven't got the fuse in line at all, and I haven't got the indicator light hooked up yet. But all of the RF parts are now mounted. I'll check my solder connections, buzz it out, and pretty quick we'll be able to do a smoke test and see if this baby works. Didn't take too long to build that. Okay, I just turned on the power supply. Everybody likes a little bit of drama. I actually did check the filament. Supply is on. I did check the filament, but and I checked that there's 350 volts, but here's the first time I've applied power. It should be warmed up now. I see the tube is lit. No smoke. Let's press the key. Oh my God, look at that. See that? Nothing has been checked. It's just working the first time. Look at that dip. Oh yeah. Okay. It's not great. It's only putting out a couple watts, but you always like to see something at least work initially. This power supply doesn't have very good regulation. I use it on my Paraset, and typically I get about 4 watts out of the Paraset with a 6V6. I'm getting 4 watts out. It is working. The crystal is heating. These HC6 crystals tend to heat more than the FT243s. One thing I did find that was very critical was the feedback, and I alluded to that here, that you would have to play with that feedback. It makes quite a difference in the way the thing operates. Depending on how you set that, it can affect the keying. Also, I originally had a radio frequency choke that was an old TV part. I replaced it with a real 2.5 millihenry, and I really didn't see any difference in output power. I would like to try a regular crystal in there and see if that cleans up the keying at all. Well, we've made some progress. So I changed out the crystal socket to an FT243 type, and the keying did clean up a little. We're still putting out about 5 watts, and we need a little better power supply. If you want to make the note absolutely clean, I would suggest putting some regulation here on pin 6, the screen grid. Perhaps 2 or 3 Zener diodes to ground if you want to go that way, or a VR150 if you want to use a gas tube to do the regulation. That would clean this up. Still a little bit of chirp on it. It's not bad though. So we've learned several things doing the project. We learned how to scale a meter, at least an ammeter. We learned how to estimate a pi network for the output. We learned how important the feedback is in the grid of the tube. And also, I didn't discuss this, but this 100 ohm and 0.5 mic capacitor, that's actually a key click filter. We don't have too many problems key down. It comes up through the choke and into the tube, and it comes up fairly gently, but they break on the key when you let up. When you let up, this network slows that down so you don't end up with a key click. So that's what's going on with that circuit. Now, is there anything I would change? I think that if I was building this again, I would dispose of the light and the on-off switch and maybe the fuse holder, and I would make the transmitter a band switching transmitter. Maybe put a band switch or a loading control here on the front where it's easier to adjust, and a band switch here, and we could do an 80-40 meter type QRP rig. The WN1LRK transmitter is alive. What a great little project. Let's put this thing on the air straight key night. I think that would be fun. Maybe we could even give it 80 meters by making the coil a little bigger. There's not much here. Very easy to convert this to 80 meters. We'll see you on the air. Okay, now I've got a regular crystal kind of hanging off the holder in the back. So it is dependent on the crystal somewhat as far as the quality of the keying. That's the way it is with these simple oscillators. It puts a lot of stress on the crystal. But we have the transmitter. It's putting out as much power as I would expect it to put out with this very weak power supply. When you key down, it goes down to almost 300 volts, and we'd really like a stiff 300. But it is working. We've got a nice little QRP rig here that, with the proper supplies, probably capable of about 6 watts out. That's not too bad for a one-tube peanut tube transmitter.